Hello everybody, I'm Spartak and we'll talk about large language models in healthcare, more specifically information extraction from EMR nodes. So let's start. So knowledge graphs in healthcare have become very powerful and popular choice. One of the many reasons is that knowledge graphs in healthcare help to organize the data in a very nice way, which provides more abilities and flexibility for the later researches. And knowledge graphs in healthcare are usually used to discover new drugs or even personalized healthcare. So here is one example of knowledge graphs. As we can see, we have multiple entities in ellipses, and the arrows between them represents the correlation and the relationship between these entities. So we have like a virus which affects somehow to gene, and then gene affects to virus, and then also gene affects to disease, and so on. So a little bit of background. So knowledge graphs in healthcare, as I said, are widely used for drug discovery, clinical trial design, and patient treatment personalization. And they help to connect medical entities such as diseases, treatments, and risk factors to create new insights. The challenges for building knowledge graphs is one of them is that these EMR nodes are usually they exist in very large amounts, and for the humans it's very hard to go over by all of them, and not also talking about the human error, human bias, and the time that it will take to annotate all of this knowledge, all of these EMR nodes. And it's usually very hard to do something with medical data when it's unstructured, and there are a lot of unstructured data in healthcare, and EMR nodes is just one of them. And one of the other challenges is that in these EMR nodes there are a lot of healthcare specific inconsistencies and jargons and abbreviations, which also needed to annotate this data. And why we chose language models? Because in the latest LLMs have shown very big potential in understanding the semantics and the meaning of the text. And usually they are very good at automatically extracting relationships between medical entities. So this is why we chose this area, and this is just a joint work with Vahan Arsenyan, David Shahnazarian, Fadi, and Dr. Kent. And this is our contribution from the paper. We provide open book question answering method and in-context learning. We also provide the guided prompt design to use the large language models, and eventually we also deconstruct the knowledge graph. So this is the models that we used in our research. As you can see, there are not a lot of models, as this paper was done a while ago, and there were not a lot of decoder-only models. So here we just chose some encoder-only models, decoder-only, and also encoder-decoder models. And we chose them by different sizes. As you can see, they are the size of the model varying from 100 million parameters to 70 or 170 billion. So let's talk about medical entities. Here you can see 4 medical entities that we used in our research. So it's the treatment, factor, coexist with, and in the middle, disease. The disease entity is going through all of the other entities, and we will use the disease entity to get information and extract from text. So the treatment is obviously going to be the methods that can slow down the progression of the disease. Then the factor, which causes, factors or risks associated with the condition. And then coexists is basically another disease that can coexist with our main disease that we are interested in. So these are going to be the entities that we will extract from knowledge graphs. And as you can see here, we have designed the questions. They are very general questions with a placeholder in them with percentage %S sign. And here we have designed 5 questions for each type of entity. So basically, when we go over all of the diseases, we will just replace the placeholder with the disease and fit this sentence question into model. So if we are interested in, so let's say cataract disease, we will say what can slow down the progression of cataract, and so on. And actually these questions are very interesting, as we saw. The design of these questions and the formulation affects some of the models and doesn't affect the others. Mainly it affects the decoder-only models, where each character is important. And we also did experiments where we tested with some subset of these questions. So like we selected 3 top questions that were answered correctly by the language model. And this is the prompt design that we experimented. Here we have 3 prompt designs. So the first one is just the basic, we can actually say it's more like open book question answering prompt, where we just provide the question, context, and then expect the answer. And then the rest are more instruction-based prompts. So one challenge that we had is that we actually need our model to answer our question only from our context. So we are not actually interested in the model's knowledge, but we would like it to have some medical knowledge. We would like it to understand the abbreviations, the jargons, or the disease or treatment names. But like in this case, for the first prompt, as you can see, the answer is very big, and it will be very hard to process that answer into a knowledge graph. As we will also need to do some post-processing to extract the main answer that we're interested in this text, which is just the first 4 letters, ARMD. So then we introduced also the traditional instruction, where we say that if the answer does not exist in the context, just answer I don't know. And for some models it worked. For some decoder-only models it doesn't work. So like in this case, I can't remember what model this was, but so here the model answers I don't know and then continues its generation, which is not ideal. But I think it's better than the first case, as we can do post-processing more easily. And the third case is more inherited from multiple prompt design techniques, where we kind of split the prompt into multiple parts, where we clearly define what we want, in what format we want, provide the template that we want it to answer, also maybe provide some examples. And the main thing that helped and improved in this case is that we also provide the entity type that we wanted to extract. So as you can see, we also provide the question type, which is coexist with, and then we say that we want to extract coexist with type from this context. And here the answer is clearly better than the rest, as we can only take the macular degeneration and vision loss, which is what exists in this context. So the data was provided by Macula and Retina Institute, and initially the data contained about 10,000 patient records of individuals with more than 122 unique eye diseases, and in total there were about 360,000 nodes, and these nodes are not in the best cleaned version, as usually these EMR nodes follow some template, and the doctors follow these templates, and most of them are very similar. So for us, it wasn't ideal to use these duplicative nodes, as we would just have the same result. So we did more filtering. We calculated the similarity between nodes and chose the most diverse nodes. And after all of this pre-processing, we ended up with 320 clinical nodes. And all of these clinical nodes we provided it to our experts, doctor experts, and they annotated all of them, extracted all of these medical terms that we can be interested in for this coexist with treatment and factor entity types. And then the evaluation, the final graph construction evaluation, is done on those annotated ground truth results with precision and recall. So this is the results. Just a quick disclaimer here, and also we also say it in the paper. We do not say that this decoder-only models don't work at all. It's just that they didn't work for our data, and the prompt design that we designed did not work for all of them. We can also change the prompt for one of the models, but it will not work for the others. So this prompt that we chose for the final evaluation just worked on most of the models, and probably it was the best for the decoder-only models as well. So here we can see the encoder-only models, encoder-decoder, and decoder-only models, and we can see that almost everywhere the FLAN UL2 model with our latest final prompt did the best. So FLAN UL2 is, the UL2 model is just the bigger version of the T5 model, and then the FLAN is the instruction dataset that UL2 was instruction fine-tuned. And here we can see that for the treatment and coexist, it did better than compared to factors, and this has some meaning because factors, usually it's pretty hard to distinguish between factor and coexist with, and we even had a case where the model classified the output as factor, but it was coexist with, although the doctor, it was not 100% sure that it can also be maybe a factor as well. Yeah, so this kind of wrong results that are not entirely wrong are very interesting. And you can see that decoder-only models did not so good as encoder-decoder models did. And this is, again, probably just because of the prompt design that we had. We were able to change the prompt design for one of these models. I think it was Wizard LM, and the results actually improved, but that prompt did not work on Llama 2 or Vicuna. So this is actually our final knowledge graph that we were able to construct from our 320 medical nodes. And this is just the table representation of that knowledge graph. We can also construct the one that I had on the first slide with all of these ellipses and circles, but it will be harder in this case to visualize because we had more than in the example we had. And here we have, with the red marked, these are the wrong answers that shouldn't be there. And then the orange marked subperitoneal fluid is the one that our model missed. So actually it was in our ground truth labels, but the model couldn't find and classify it as factor. Yeah, and actually we also had one very interesting case. So we focused on this, in this research we focused on only one disease, which is age-related macular degeneration. But in our factors, as you can see, we are, and actually no, in the coexist, we are missing the disease called cataract, which is another eye disease. And one of the models classified the cataract as coexist with, and the intuition was that the surgery that are done for the ARMD can also cure the cataract, but that is not always the case. So our experts had a bit of disagree in this. Yeah, and our most key takeaways are that EHR nodes contain valuable information that are often being ignored or missed by the human annotators, and that the decoder-only models, especially the new ones, require further investigation for this relation extraction task. And we believe that this method or this approach can help to contribute novel discoveries by highlighting existing relationships between entities that were existing in the books but overlooked or missed by the humans. Yeah, so this was it. If you guys have any questions.
I think the problem is that part. How do you calculate recall? So as far as I understand, for some of these diseases, you know some ground truth, right? You know that someone told you that this is a factor for this. But what if there is some new factor that you didn't know and you want to discover?
Yeah. So in this evaluation, we only take the ground truth, only the entities that are annotated by our doctors. So we ignore everything else. So even if this entity exists or this relationship exists, we ignore and classify it as wrong.
I see. So if you have these annotations, then you are measuring which percent of it is covered by language model when that's recalled.
Yeah.
And how many of the covered ones exist in the annotations of the position?
Yep, correct.
And one more, do you continue this work or?
We are planning to do this evaluation for the all new models, including Gemma and Llama 3. But the main focus will, I think, stay in this one.
I see. That's what I was saying. I think the hard open source models are not pretty good. I realize that you avoided to use GPT-4 or something to keep it open, but yeah, these recent ones should be very strong, but it might require a lot of prompt engineering.
Yeah.
Okay, then. Thank you for the interesting presentation. And I hope to see the application of this technique in other problems such as gene pathway and disease relation. For example, cancer. Which pathways are responsible for a specific type of cancer? This would be very interesting.
Yep.
Thank you.
Thank you.